Hey, I'm Manav, and for my final project for Math 2700, I decided to create a talk on the Laplacian on fractals. To begin, let's start by talking a little bit about what the Laplacian is. The Laplacian, or the Laplace operator, is a differential operator, and it's the divergence of the gradient of a scalar function. We denote it using a nabla square. So Laplacian is really important when you're trying to do any kind of analysis on manifolds. In manifolds, we can think of them as being a topological space that's equipped with a coordinate system, though that's not the most precise definition. And in these cases, the Laplacian is useful because it commutes with translations and rotations. That is, if you have a function f, you can translate it or rotate it by composing it with the function given here is t, and the Laplacian after that composition is the same as composing it, the function, with the Laplacian of f. So the usual Laplacian requires coordinates to define the partial derivatives and the gradient. And you'll see here in a second that that becomes a little bit problematic when you're dealing with fractals instead of manifolds. So fractals, what are they? Fractals are geometric structures, and they're typically characterized by self-similarity, detailed structure at arbitrarily small scales, and local irregularity that can't be described using traditional Euclidean geometry. Fractals are not manifolds, and they don't have a well-defined coordinate system. And as we know from talking about the Laplacian, that becomes a little bit of an issue. So we can instead try to determine an analog to the Laplacian that we can apply instead to fractals. So an example of a fractal, probably the most famous example out there, is the Sierpinski gasket, and it's a fractal that we construct as a colimit over a particular sequence of graphs. And you can see the first three graphs are shown here. All right, so let's get into constructing an analog for the Laplacian that we can use on fractals. So to generalize the Laplacian, let's consider a property that it has. So it has a property that when the Laplacian of u equals f, the following identity holds, where v is any valid function in the domain, and mu is an appropriate measure. And e of uv is what we call the Dirichlet form, and that's defined on a manifold M by E of uv is the integral along M of the dot product of the gradients of u and v, of course, with respect to our measure mu. So in our first attempt, we can try to use this as the defining property of the Laplacian on fractals. And this would, of course, require us to define a Dirichlet form and a suitable measure. Here, we're going to use the Hausdorff measure in a way that doesn't require coordinates. Okay, so the Dirichlet form for graphs. As we saw in our earlier example with Sierpinski gaskets, fractals can be approximated with a sequence of graphs. And so let's try to define the Dirichlet form on each graph gamma sub m, where m is just the number iteration of the graph. So if we discretize the equation on manifolds that we got previously, we'll get that E sub m of fg is equal to the sum along all of the vertices adjacent to y. The little tilde symbol there denotes an edge, hence the adjacency, of f of x minus f of y times g of x minus g of y. Following those constraints. Okay, so our ultimate goal when we're defining this Dirichlet form is for the limit to exist where m approaches infinity of E sub m of fg. And for that to happen, we need to scale E sub m by the appropriate constants C sub m. In our example of the Sierpinski gasket, this constant is equal to 5/3 to the power m. And there's a long and drawn out process of determining that that's the case for the Sierpinski gasket that we don't need to get into right now. So you'll see that now we define E sub m of fg as the same sum that we had before, only this time we're scaling it by the non-zero constant Cm. And now we can finally determine that limit as m approaches infinity, and we define that as E of fg. And that is our Dirichlet form for graphs. So now that we've defined that and we have a suitable measure, again, we're using the Hausdorff measure here, we can construct our Laplacian analog. So finally, we have a pointwise formula for the equation of the Laplacian analog. And that is that the Laplacian of u of x is equal to the limit as m approaches infinity of 3/2 to times 5 to the m multiplied by the sum along all the vertices adjacent to x, connected by edges, of u of y minus u of x. And note here that this equation for the Laplacian analog is specific to the Sierpinski gasket. What does remain the same, though, is that sum there. The only thing that changes from fractal to fractal is the constants that you multiply the sum with within the limit. Okay, so now let's think about one of the primary properties of the Laplacian analog we've just constructed, and that is harmonic functions. So let's start by thinking about harmonic functions in manifolds versus in fractals. So you can recall that a harmonic function on a manifold is defined as one whose Laplacian is 0. And extending this definition into a theorem for harmonic functions on manifolds, we find a property that their value at any point is the average value of a ball centered at that point. In other words, the average value of the neighborhood of points. So in the case of fractals, we can take this theorem as a definition and say that a harmonic function on a fractal is one whose value at every non-boundary vertex is equal to the average value of the neighboring vertices. And given that definition, we can attempt to determine the definition on manifolds, that is, that harmonic functions on manifolds are the ones whose Laplacian is 0, into an analogous theorem on fractals. And here we have a proof of that. So let's look again at the fractal Laplacian we determined, and of course this is the one that's specific to the Sierpinski gasket, but you'll see here that the constant that you scale it by don't actually matter when proving this theorem. So the Laplacian is 0 if and only if that sum is 0 because it is scaled by non-zero constants. So given that sum equals 0, let's pull the u of x out of the sum and add it to the right side of the equation. And so we can pull it out by multiplying it by the number of vertices adjacent to x, because if you'll remember, that's the number of y's we have in that sum. And if we solve for u of x, we have that the sum of the vertices adjacent to x, so the sum of the number of y's times u of y over the number of vertices adjacent to x. And you'll notice that this looks eerily similar to an average value function, and that is the exact condition for a function u of x to be a harmonic function. And we can work through this the other way around and go from the theorem to the definition as well. Okay, here's an example again of the Sierpinski gasket. And this is a harmonic function on the Sierpinski gasket, and it has boundary values of 0, 0, and 1, and that's pictured right here. Okay, concluding thoughts. So in summary, we defined the Laplacian and explored its importance in manifold analysis. We defined fractals, how they differ from manifolds, and identified the need for a modified Laplacian. We constructed an analog Laplacian for fractals and explored harmonic functions on fractals. Of course, we're barely scratching the surface of this massive field, and we can do quite a lot more with the fractal Laplacian, such as studying its eigenfunctions, solving the heat and wave equations on fractals, and studying post-critically finite self-similar fractals. Here are the papers and books that I referred to when creating this talk, and thank you for listening.